So we'll be working today on Sousa's car crash. So we're given the problem that Mr. Chakran is sightseeing at the edge of a cliff when Mr. Sousa suddenly slams on his brakes, crashing into Chakran's car, causing the two to inelastically collide and fly to the bottom of the cliff. We're asked to determine if Sousa's car was speeding when it was first taking off. The video gives... live!
There we go. We're going to default to your right. Oh my God.
It's coming right for us! Here comes Mr. Sousa. Oh, down the cliff they go. That video was just a quick example of what Sousa's car probably looked like. Just like those rednecks, Sousa doesn't know when to hit the brakes. So here we have Mr. Chakran's 2000 Jeep Cherokee. Mr. Chakran says that he was probably sightseeing, but that thing's so old it's probably broken down. Despite its 200,000 miles, the thing still has a mass of 1,524.070 kilograms. Sousa was feeling adventurous today, so he thought he would test drive a fine, high-quality automobile such as the 2000 Hyundai Elantra station wagon model. This luxury vehicle comes fully loaded with a tape deck and roof racks. With its sleek appearance, the wagon comes in at 1,216.081 kilograms. It was a beautiful day, the day of the accident. Not a cloud in the sky, about 70 degrees. And perfectly dry roads. After some investigation, one finds that the coefficient of friction in these roads is 0.7. But this day took a turn for the worse when Sousa couldn't see Chakran stopped ahead. Looking at the scene of the crime, Sousa braked for 0.278 meters. The cars then fell 0.95 meters off the cliff and then landed 1.2 meters away from the cliff. It was given that the weight of Sousa's car and the model was to scale with the accident. To determine a scale, one must establish a ratio of actual divided by diagrammed. In this case, we have the mass of Sousa's car over the mass of the toy car. The scale we determined was 38.6963. Any other measurement that we take from this point on is off of this ratio. So to use this ratio, we multiply each of the diagram models by 38.6963 to determine the actual value of the measurement. So we know we need to determine Sousa's velocity before braking. But with the data that we are given, we can only begin to find the data at the end of the crash. After studying the motion of the two cars, we find that it is represented by a projectile. As you can see, here comes a projectile. Once we know that it's a projectile, we must come up with a table for the vertical and horizontal axes. For the vertical displacement, we have a height of 36.7615 meters, found by multiplying the model vertical displacement by the scale. We know that prior to the collision, the projectile of Susan Chakran's car had no velocity, and as always, the acceleration due to gravity is 9.8 meters per second squared. In the horizontal, we know that the object landed 46.436 meters away from the base of the cliff. So we need to find the time of flight and the impact velocity. Looking at the available variables at this point, we can only solve for t. Given the vertical height, the vertical displacement, initial velocity, and acceleration, we know that we must use the second kinematic. So we must solve for t, so our equation looks more like this. After you plug in the values, you can plug in the values. This is algebra, so you should be able to do it yourself. And you should get a time of 2.739 seconds. We're going to keep a couple extra sig figs here because you're going to need them for later. So now with having solved for t, we can determine the impact velocity by studying the horizontal motion. Impact velocity is found by dividing the horizontal displacement by time. So we're going to have quite the impact velocity here. Plug in your values and you should get an impact velocity of 16.9563 meters per second. Again, we're going to keep a couple extra sig figs here. So now that we've found our impact velocity of the projectile, we are already and since we already know its mass, we have what looks to be a conservation of momentum problem. So looking at the two cars that were separate and now together, we have an inelastic collision, or a big fish little fish problem. So we know in an inelastic collision, the mass of Sousa's car times the velocity of Sousa plus the mass of Chakran's car times the velocity of Chakran's car is equal to the mass of Sousa Chakran car times the velocity of Sousa Chakran car. We need to solve for the velocity of Sousa's car, so this will be his speed prior to crashing into Chakran. After plugging in the values, we have a speed of 38.2009 meters per second. Since we now know that Sousa's speed prior to braking, we can find his speed before he hit the brakes. Prior to the brakes, Sousa's speed is all kinetic energy, but the friction between the brakes and the road creates thermal energy, so the final energy is both kinetic and thermal. The law of conservation of energy states that initial energy is equal to final energy. So, in this case, we have kinetic energy, which is equal to the kinetic energy plus the thermal energy. We know the equations for kinetic energy, which is 1/2 mv squared, and the equation for thermal energy, which is mu k Fn times d. D in this case would be the distance of the skid. So would set up the equality, and you can plug in your values now. We're solving for the V naught, so you're going to isolate the V. Have that work down there. Plug in your values, and you should get 14.996 meters per second. So the initial equation was given to us in miles per hour. So we still have the question, was he speeding? So we could take that 14.996 and use a conversion factor for converting to miles per hour, but you know what? Usually it's a lot easier to go to Google, so let's do that right now. .996 meters per second to miles per hour. And that's 33.54. So looks like we do have a speeding in this case. Well, I hope this helps.